It sits 68,000 parsecs from a comfortable answer. No, that number is wrong. It sits 190 light-years from Earth, close enough to see with a cheap telescope from your backyard on a clear night if you know exactly where to look. And for over a decade, it was old enough to break physics. Not old in the way we usually mean it. Not ancient like a redwood, or ancient like the pyramids, or ancient like the first cave paintings scratched into stone by hands that have been dust for 40,000 years. Older than that. Older than everything. Astronomers pointed their instruments at a single, unremarkable point of light in the constellation Libra, and the math came back impossible. The star appeared to be older than the universe it was floating in. Stay with me, because this isn't a metaphor, and it isn't clickbait. This is a real measurement, made by real scientists, using real telescopes, that appeared to violate one of the most basic rules of cosmology. Nothing can be older than the thing that created it. This is the real story of HD 140283, the star they call Methusela. The star itself isn't new. It was catalogued generations ago, a faint, high-velocity subgiant drifting through the outskirts of our galaxy's halo, the sparse, ancient region that surrounds the crowded disk where most stars, including our sun, are born and live and die. But the crisis didn't begin with the star's discovery. It began with a number. In 2000, astronomer Don Vandenberg and his colleagues used newly available stellar models to estimate the star's age. The number that came back was staggering, roughly 16 billion years old. For context, the universe itself, according to the best cosmological measurements available at the time, was approximately 13.7 billion years old. A star, 2 billion years older than time itself. Nobody expected this. In 2013, the Hubble Space Telescope entered the story directly. A team led by astronomer Howard Bond used Hubble's fine guidance sensors, instruments designed to lock onto guide stars with extraordinary precision, to nail down HD 140283's distance with unprecedented accuracy. Bond and his team combed through 11 separate observation sets, recorded between 2003 and 2011, measuring the star's position against the sky with a precision fine enough to detect its parallax, the tiny telltale wobble that reveals exactly how far away a star truly is. The refined distance changed the picture, but it didn't solve the problem. Bond's team calculated a new age, 14.46 billion years, with an uncertainty of roughly 800 million years. Even accounting for the margin of error, the star was still uncomfortably suspiciously close to being older than everything that exists. 2 independent research efforts, 2 different decades, 2 different sets of instruments. The same unsettling conclusion kept surfacing. This star doesn't fit the timeline. To understand why this mattered so much, you have to understand what a star's age actually represents. A star isn't just a ball of burning gas. It's a clock. Stars form from collapsing clouds of hydrogen and helium, the raw material left over from the Big Bang, cooked slightly by the first few generations of stellar furnaces. The heavier elements, carbon, oxygen, iron, everything that makes up planets and blood and bone, didn't exist yet. They had to be forged one star at a time in nuclear furnaces and supernova explosions, and then scattered back into space to seed the next generation. That means a star's chemical composition is a fingerprint of when it was born. HD 140283 is what astronomers call metal poor, meaning it contains almost none of those heavier elements. In the language of stellar astrophysics, this star is chemically primitive. It looks, in its composition, almost exactly like it should if it formed within the first few 100 million years after the Big Bang, one of the very first generations of stars to ever exist, 13.8 billion years. That's the age of the universe, according to the Planck satellite's precision measurement of the cosmic microwave background, the faint afterglow of the Big Bang itself, still detectable in every direction we look. If HD 140283 really was 14.46 billion years old, the math simply didn't work. You cannot have a star older than the cosmos that produced the material it's made of. It would be like finding a photograph taken before the camera was invented. Every possibility had to be considered. Was the distance measurement wrong? Was the stellar model wrong? Was something fundamentally broken in how we calculate cosmic age at all? The scientific stakes were enormous, not because of one strange star, but because of what it implied. If Methusela really was older than the universe, one of 2 things had to be true. Either our models of how stars age were flawed at a fundamental level, or our understanding of when the universe began was wrong. Neither option was small. What followed was a decade-long forensic investigation, conducted not with fingerprint kits and interviews, but with spectrographs, interferometers, and increasingly refined mathematical models, each one narrowing the range of possible ages, inch by inch, year by year. A follow-up study in 2014 pushed the estimated age even higher to roughly 14.27 billion years. If anything, the crisis had deepened. The margin for error was calculated at roughly 700 to 800 million years, meaning that at the outer edge of uncertainty, the star could still just barely fit inside the universe's timeline. But barely fitting inside a box isn't the same as comfortably fitting inside it. Something still felt wrong. Then, in 2020, a team led by astronomer Anna Karovakova turned to a different kind of instrument entirely, the Kara Array, a facility that combines light from multiple telescopes spread across a mountaintop in California to achieve resolution far beyond what any single telescope could manage, a technique called interferometry. Instead of estimating the star's physical size indirectly, Karovakova's team measured it almost directly by observing the star's actual angular diameter in the sky and combining it with its known distance. The result? A smaller, more precise measurement of the star's radius than had ever been achieved before. And a smaller radius, it turned out, meant something significant for the age calculation. Meanwhile, in 2021, researchers Janling Tang and Meredith Joyce, working at the Australian National University, took Karovakova's improved measurements and fed them into an advanced stellar modeling software suite called MESA, Modules for Experiments in Stellar Astrophysics. This wasn't a simple recalculation. It was a full simulation of the star's entire life cycle, run again and again across a huge grid of possible masses and compositions, searching for the exact combination that matched every observed property of the real star. Its brightness, its temperature, its size, its chemistry. The number that emerged from that simulation, 12.01 billion years, with an uncertainty of just 50 million years under ideal modeling conditions, or, accounting for broader systematic uncertainties in the models themselves, 12 billion years, give or take 500 million. Just like that, the paradox that had haunted astronomers for over a decade appeared to dissolve. 12 billion years fits comfortably inside a 13.8 billion-year-old universe. No contradiction, no broken physics, case closed, except it wasn't. When researchers looked again in 2025 using an entirely different method, asteroseismology, the study of a star's internal structure through the tiny oscillations rippling across its surface, essentially listening to the star's internal heartbeat, they arrived at yet another number. Their result, 14.2 billion years, with an uncertainty of roughly 400 million years. Once again, the star was pushing right up against the edge of the timeline, once again technically inside the margin of error, but only just. 4 independent investigations, 4 different techniques, theoretical modeling, Hubble parallax measurements, ground-based interferometry, and asteroseismic analysis. And instead of converging cleanly on one settled number, the age of HD 140283 kept sliding back and forth across a range spanning nearly 3 billion years, sometimes comfortably inside the universe's age, sometimes uncomfortably close to breaking it. You need to understand what that actually means. This isn't a case of scientists disagreeing over sloppy data. Each of these results came from careful, peer-reviewed, methodologically rigorous work. And yet the answer to a seemingly simple question, how old is this star, kept refusing to fully settle. This is where the story could have ended, quietly, as a solved problem. A star, once thought impossible, brought back within the bounds of a sensible universe through better instruments and smarter models. But not everyone was satisfied that the problem was fully closed. Some researchers pointed to something more unsettling hiding underneath the numbers. Nearly every one of these age estimates depends on assumptions about how convection works inside a star, the churning, boiling motion of plasma that carries heat from a star's core to its surface. Convection is notoriously difficult to model. It's turbulent, three-dimensional, and chaotic, the kind of physics that resists clean mathematical description. Most stellar models, including the ones used to calculate HD 140283's age, still rely on simplified one-dimensional approximations of convection, because fully simulating the real three-dimensional turbulence inside a star is almost prohibitively expensive, computationally. Tang and Joyce's own 2021 paper, the one that produced the reassuring 12 billion year figure, explicitly noted that their results carried implications for how we handle convection modeling. In other words, even the study that appeared to resolve the crisis was quietly flagging that the underlying method still had soft spots. If our convection models are subtly wrong, even in small, hard-to-detect ways, then every age estimate built on top of them inherits that error, not just for HD 140283, for thousands of other stars used as cosmic benchmarks across the galaxy. That's the deeper theory some researchers have raised, that Methusela isn't just a strange outlier. It might be a warning light, a single star, by chance positioned close enough and bright enough for us to measure with extreme precision, exposing a small but real crack in the tools we use to measure the age of everything. If that's true, the Methusela star isn't a solved mystery. It's a messenger. It would be irresponsible, though, to leave you with the impression that mainstream astrophysics is quietly panicking over a hidden crisis in cosmic dating methods. It isn't. The overwhelming consensus among astronomers today is that HD 140283's age, properly accounted for with realistic uncertainties, is consistent with the age of the universe. Not suspiciously close, not barely surviving, consistent. Howard Bond, whose Hubble-based measurement first seemed to deepen the crisis back in 2013, made this point directly. Once you account for every source of uncertainty, both in the observational measurements of the star's distance and brightness, and in the theoretical uncertainties baked into stellar aging models, the error bars widen to roughly 700 to 800 million years. Within that widened range, there simply is no conflict. The universe's age of 13.8 billion years sits comfortably inside the star's plausible range, not outside it. The more recent astroseismic study, which produced that 14.2 billion year figure in 2025, reached the exact same conclusion in its own analysis. The authors were explicit, even though their central estimate sat slightly above the universe's age. The difference was well within statistical noise, less than one standard deviation. Their own paper stated plainly that the result was not in real tension with cosmological age, and that realistic uncertainties for a star at this evolutionary stage may run even higher than their formal error bars suggest, potentially by another 10%. In plain terms, every time scientists have measured this star more carefully, the apparent paradox has narrowed, not widened. What looked in the year 2000 like a 2 billion year contradiction has been steadily whittled down, refinement by refinement, into something well inside the boundaries of ordinary measurement uncertainty. This is, in many ways, a genuine science success story, not a cover-up, not a stretch, but the slow, careful process of instruments and models catching up to a hard question. Better parallax measurements, better radius measurements, better stellar physics, each one shaving the uncertainty down, bringing an impossible star back into the realm of the possible. Everything changed, not because the universe rewrote its own age, but because our tools got sharp enough to see the star clearly for the first time. And yet, even granting that the paradox has been resolved on paper, something about the Methusela story lingers, because the resolution didn't come from a single decisive measurement. It came from 4 different techniques using 4 different assumptions, producing 4 different central values, spread across a range of nearly 3 billion years, and it was only by carefully stacking uncertainty upon uncertainty that those 4 answers were shown to technically overlap. That's not the same as one clean number confirmed by independent replication. That's 4 separate estimates, each with its own hidden assumptions, that happen, barely, not to contradict each other once you account for everything that could possibly be wrong with each of them. Which raises the uncomfortable question underneath all of this. How many other settled cosmic ages are resting on the same kind of narrow, assumption-dependent agreement? HD 11402883 isn't unique because it's the oldest star in the universe. It almost certainly isn't. Plenty of ancient metal-poor stars exist scattered through the galactic halo. It's unique because it happens to be close enough and bright enough for us to measure with a level of precision we simply can't achieve for most other stars in this ancient population. In other words, we got lucky. We had one star, close enough to interrogate thoroughly, and even with every modern tool at our disposal, Hubble's fine guidance sensors, ground-based interferometry, advanced stellar modeling software, and the internal seismic rhythms of the star itself, we still couldn't pin its age down to better than a range spanning roughly 2.5 billion years. If that's the best we can do for the one ancient star we can study up close, what does that say about the thousands of other ancient stars scattered across the galaxy that we can't study nearly as well? There's a strange kind of humility built into this story. We live inside a universe we've dated to within a fraction of a percent of accuracy, 13.8 billion years, measured through the cosmic microwave background with extraordinary precision. And yet a single star, orbiting quietly in our own galactic backyard, has spent the past 25 years testing the limits of how confidently we can actually make that claim stick at the level of individual objects. HD 140283 isn't a monster. It isn't an anomaly demanding a rewrite of physics. By every current measurement, it is exactly what it appears to be. One of the very first generations of stars ever formed, born in the early, chemically pristine universe, still burning quietly nearly 14 billion years later, close enough for us to watch. But it is also a reminder of something larger, that the tools we use to measure the deep past, whether we're looking at a single ancient star or the universe as a whole, are only as good as the assumptions baked into them. Every refinement to Methusela's age came from questioning something we thought we already understood. The star's exact distance, its exact size, the physics churning invisibly beneath its surface. And somewhere out there, past the edge of what our instruments can currently resolve, there may be other stars, older, stranger, harder to measure, quietly waiting to test those same assumptions again. If you want to understand how astronomers are now hunting for the very first stars that ever existed, the true population 3 stars, forged directly from the raw hydrogen and helium of the Big Bang itself, and never yet directly observed, that's a story for another day. Stick around for it. Because if one nearby star could make scientists question the age of the universe for over a decade, it's worth asking what else is still hiding in plain sight, waiting for someone to look closely enough.